Perfect. Okay. We're going to continue on here, and I wanted to start with one question that came up in kind of our interlude, which is a clarifying question on the number of balancing dampers required for a terminal with chilled beams in series. And so I'm going to kind of draw a mental picture for us here of a VAV box serving 3 chilled beams. The furthest chilled beam, the longest run of duct from terminal to chilled beam, would have no balancing dampers. It would have a single duct only. The 2 other beams that are closer and would be receiving a higher static pressure from the ducted system would require a single balancing damper each. We wouldn't have another balancing damper upstream in like a branch takeoff or anything. We would need whatever number of beams we have, -1 would be the number of balancing dampers, unless duct symmetry allows 2, to both have equal pressure at the furthest point away. So some duct symmetry can help us out. Usually what I'd recommend is just specifying and laying out a balancing damper at every beam except for the furthest one away. So we're going to move on to considerations for DOAS terminal selections here. There's a lot of topics we're going to go through. And for sake of time, we're going to dive right in because these first few slides are ones we've already seen, so I can be very brief with them, which is good. I'm focusing on this product in particular in this presentation, the fan-powered chilled water terminal. We're going to talk about some of the benefits that it can provide to a DOAS system, some of the unique things it can do. We're going to talk about a few other DOAS type terminals that are latent capable, so fan and blower coils, and some of the design philosophy that goes behind that. And then we're going to talk about some other considerations like acoustics and like reheat, especially in the scope of reheat, now that we're being very considerate of decarbonization and electrification and low entering water temperatures and all the hurdles about that. So those are kind of general terminal topics too. But the vehicle for talking about it is this product here. So once again, this product is sensibly cooling air through its return. We have an offset in volume between the fan and the primary air damper. That offset is induced through the coil on design day for heating in the summer, or for cooling to offset design day in the summer. We're able to measure and control primary airflow with our fresh air inlet, which has a full cross-flow sensor and damper, which is going to allow for demand-controlled ventilation. And mandatory on these products is EC motors. EC motors, for the most part, are being viewed as mandatory anywhere we're using fractional zone-to-zone motors because they're so much more efficient. However, their longer lifespan, their higher capabilities for static pressure, and their capabilities to sequence and change their volume set point throughout operation are all humongous assets. So lots of considerations there. Now, I referred to how optimized these are for variable loads, but I like to give a metric to that. And the reality is for our standard height series fan-powered DOAS box, we're looking anywhere from a 10 to 24 to 1 turn down ratio for the fan. So extremely significant. Now, would I ever recommend a 24 to 1 turn down ratio for a fan? Absolutely not. But what this does mean is we can have a 2400 CFM unit that could turn down to 1600 CFM, or we could have the same casing size at a design day set point of 1600 CFM for an acoustically considerate application that can still turn down to 800 CFM. So really good benefits, although generally for a fan, 4 to 1 turn down is kind of about the maximum that I see. And I generally like for a fan a 2 to 1 turn down ratio, because keeping the fan elevated is actually beneficial because it's not as annoying for an occupant to hear a huge variability in fan speed. And we're also getting more mixing to the space, which can actually help air distribution and keeping us in deadband for longer, because we're just mixing room air. We're also filtering that room air, so we're going to improve indoor air quality a lot as well. For the primary air damper, an 8.5 to 1 turn down ratio is my rule of thumb because that covers all of them. And that 8.5 to 1 turn down ratio is also large. I would generally recommend. I like a 4 to 1 turn down ratio as a maximum rule of thumb for a VAV damper inlet. And usually that's 2,000 feet per minute down to 500 feet per minute as a pretty solid design rule of thumb. So I like to talk a little bit about the history of this product because I think it's interesting. It came from the DMV area, so DC, Maryland, Virginia. And the rationale for it, or the reason why it originally came up, was because the Pentagon was doing a retrofit, and being a historic building with low plenums, not being allowed to be built very tall because of all the other historical buildings in the area, they needed something that could fit in a foot of plenum height, but that could provide like a LEED high level certification as far as energy efficiency went. And they actually really wanted to go with chilled beams. But because of some restrictions in the ceiling and the fact that they actually had some historic ceiling materials that they didn't want to end up ripping out and doing things like that, they couldn't go with chilled beams. And so the low profile version of this product was developed. Now, this low profile version of the product existed for about a decade before Price was the first manufacturer to offer a standard height version. We first released this in 2018, and since 2018, the market size for this product has doubled year over year. So it's becoming very swiftly accepted and popular, generally in occupant-driven environments, so where the occupant's load drives latent and often is driving sensible, especially on internal zones. We also see it with a lot of office environments in particular, especially from the top 5 companies in the world. They're all using this product for their offices. So the Amazons, the Googles, the Apples, the Microsofts, in particular, really like this product for their Class A office space. I like to talk a little bit about the flexibility of the reheat options. I know I referred to this before. When we think about a historical hot water coil on the discharge of a terminal unit, they were designed for 180 to 140 degrees of entering water. That's how their circuitry was laid out. That's how their sizing, fins per inch are all laid out. And that would allow for a 1-row coil for 180 water, 2-row coils for 140 degree water. That's what we see most people specify and utilize most of the time for reheat coils. Now, in the wake of further decarbonization and electrification, the utilization of air source heat pumps, we're seeing 120, we're seeing 110. I saw a project with water source heat pumps in Seattle that had 96 degree entering water. We can't do that with the typical coil anymore, so we need another alternative option. Maybe we do a 4-row coil. That's not ideal for pressure, watts per CFM. So maybe instead we'd use electric coil discharge reheat. Very low pressure drop, very high capacity, very immediate response to a call for heat. Not loved by every market, so a good solution, but dependent on the locality, whether or not it can and will be used. So the other alternatives to use are very large coil on the return, that's much bigger, that has much longer tube runs, and that's going to allow for better capacity with lower air pressure drop. This could be a 4-pipe solution, or it could be a 6-way valve hot-cold changeover solution. Both exist, both have been utilized, both are pretty familiar and comfortable in some different markets. Now, this coil on the right is often something like 15 by 16 inches, while the side coil on the left is 18.5 by 31.5. So we're seeing more than a doubling in face area, which is going to reduce pressure drop and work a lot better for low entering water temperatures. Any questions? Okay. I just saw a question about a 6-way valve or 2 3-ways. If we're doing a hot-cold changeover with only 2 pipes, we're seeing a 6-way valve most frequently and most commonly. If we were to see, constant fluid volume for 2 separate coils, 2 3-way valves would be more common. Some questions or some other additional benefits of fan-powered chilled water terminals. There's kind of 5 highlights I want to show on screen here. So one is the capability of some higher humidity applications due to the fact that we have high variability to the primary airflow rate. An application comes to mind in particular, which was a high-performance school that had a small lobby area, but it did have air infiltration. And rather than needing to get a fan coil that could do latent cooling, what they actually looked at doing instead was they kind of sized what would be their typical design day based off of ventilation rates for the space. And then they sized a higher ventilation rate for dehumidification purposes. And if they needed, they could elevate just that one zone up to dehumidify the space. Of course, it was appropriate for what was laid out for that school. It wasn't a huge facade, massive amounts of air infiltration. It was the right amount to take that kind of approach. And of course, a fan coil is another alternative that would work well. Although another thing we see, which is the bane of my existence, but I do see it, is operable windows in DC on spaces that have sensible only applications. And sometimes they'll also have a sequence which ramps the airflow up into the space to dehumidify those zones. And they'll do that with a relative humidity sensor and a sensor on the windows. So if the window does get opened, they throw a bunch of air in there and waste a lot of energy, but keep it dry. Not ideal. Not my recommendation. We don't need operable windows in high-rise office buildings, especially not ones that we want to do dry cooling. So we can get demand-controlled ventilation, which I'll talk about more in a few slides. The fan operation allows for morning warm-up and night setback, so we can turn off that localized air handler. We can still recirculate locally, which means we can warm up the building in the winter months. And if we're looking in summer months and we needed to cool it down, that's not really common, but I guess you could do that. Usually the chiller is going to be off at night in most cases. Fanner operation is also going to reduce that zone stratification. So I kind of referred to that, but keeping a higher ratio of fan airflow during deadband, because the EC motor has such low power consumption anyways, we can turn over a lot of airflow in deadband, which is going to keep the space mixed and keep it more comfortable for longer. It's actually often going to result in better energy efficiency because we don't stratify the space and kick in heating when we have enough heating in the zone, or kick in cooling prematurely. And then the high static for the fan motor allows for a diverse set of outlet options. So whether we want architectural slots, we can really do anything that you can do with the VAV box with this terminal. So that allows for a lot of flexibility. So I want to speak to sequencing briefly here as well. And when we sequence this product, the one thing I like to really bring up, which is going to lead us to demand control ventilation, is just the counterintuitive nature of some of the sequencing. So what we're looking at here, and we actually just have outdoor air cutoff on the bottom, but it's not consequential to this slide, so you don't have to worry about it too much. You can refer to your slide deck if you want to see what's going on there. But what we have here is a sequence diagram. So the middle of this diagram is our temperature set point. As we move 1.5 to 2.5 degrees to the right and the left, that's the end of our dead band. So that's where we don't want the system to start cooling or start heating. We're allowing some drift because the occupant probably can't actually tell 2 degrees of difference. So whether it's 70 or 72, who cares? Whether it's 72 or 74, who cares? If our set point's 72, we're going to let it drift a bit. And that's going to allow for really less switching of electrical and mechanical components, which is going to improve lifespan of the building, and it's also going to reduce energy costs for the owner. When the space does get too hot, we're going to need to cool it down, and the way we do that first is hydronics, typically for this kind of product. The reason for that is if we look at the first stage of heating, the first thing we do is air. The rationale is the zone is probably stratified, the ceiling is going to be a little bit warmer. So if we increase our fan energy and mix more air down into the space, that air is probably a degree or two warmer, and it's going to make the space more comfortable. That's why we do hydronics first for cooling, although there could be some staging where they both vary just at different slopes and outpace one another. When we move towards the second stage of heating, that's where we pull in our electric coil or our hot water coil or whatever else we may need. Perimeter reheat from other fin tubes, there's lots of options. But generally, this is the kind of relationship we see, which is a little counterintuitive, so I like to point that out. This is a decoupled system, so by nature, that means we're going to control the fresh air in a decoupled fashion from the hydronics going through the coil. And the way that this works for us here is generally measuring based off of carbon dioxide levels or occupancy levels within the space as well. So I referred to the Nest Home thermostat. Infrared's a big way. Badge counting is a big way. The most common is measuring and controlling based off of carbon dioxide concentrations. So we have on the left of the screen a conference room. Let's pretend this is the room we're in. I was sitting in here this morning. It was just me, Dean, and Sean for a little while. Then we had Chris and Matt show up. Then we had all of you show up. The space became more occupied. We're breathing, we're sweating. Maybe someone was burping. Chris, was that you? No, it wasn't, Chris. And that releases more carbon dioxide into the zone. We measure that concentration of carbon dioxide. We add more ventilation air to offset it, and the space stays well ventilated and more comfortable as well, because we're also providing latent heat to the zone through those actions as well. And demand control ventilation is a perfect example of, if we want to control something, we need to measure it. So we want to control indoor air quality. Great. Let's measure something that is correlated to indoor air quality. So we measure carbon dioxide. Any questions on demand controlled ventilation? Okay, that's a very basic example, but it helps to frame it. So a couple real world examples of systems that use this type of product. Midtown Center in Washington, D.C. We can see the low floor to ceiling height. That's because this is close to the Washington lawn and nothing can be built taller than the Washington Monument. That means a 6-story traditional building is a 7-story building in D.C. They get 12 inches of plenum height. They crunch everything down. Their design engineers hate their lives. Sounds fun. So that's the approach there. So that's an 11-inch tall box, which is why it's a little shallower, and that's why they see a lot of open ceiling designs. Other real world examples, I think we have about 6,000 of these installed at the new HQ2 in Amazon, and about 8,500 of them installed in the Microsoft Campus Modernization Project in Seattle. 2 projects I got to work on pretty closely, which was fun. I left this rendering. That spire never got permitted and never got built. The 3 surrounding buildings are all built. But that was what they originally dreamed up for Amazon HQ2. I left it in because it looks so cool. I wish they ended up making it. I'm not surprised that they didn't. I think that would have been in the like top 10 architectural wonders of the world at that point if that thing had actually gotten built. But I still like the render. So another example, and this is more local to you guys in the Northeast. This was actually designed by BR+A, is New York University in Manhattan. And this project actually used latent options and sensible options. They used a lot of high-grade filtration and custom silencers to achieve the design goals of New York University in a very unique way. And so this was used on that project throughout. And so to spotlight a couple of the other products that could be used in this type of application, but maybe are a little bit more flexible due to the fact that you can actually do latent cooling with them. One that I like to recommend is our FCHG, the horizontal low profile high performance fan coil. At Price, we often like to name things based off of acronyms for the model codes. So SDV, our single duct. Does anyone know what that stands for? SDV, any guesses? So S, single duct, V, variable volume. D is actually digital for digital controls. We used to have an SPV for pneumatics and SEV for electronic controls. We also used to have a FCHCHCLP, and we changed that to the FCHG because that was a stupid name for a product. So G stands for Genesis, which is a brand name for this type of product, because of course nobody's going to ever write down base of design as FCHCHCLP. So we kicked that one. So this is a product that fits a nice niche in the market. Generally, I see it actually specified and laid out up to about 2,000 CFM for acoustical purposes, because it's often getting used in acoustically considerate environments that have a shorter plenum height. It is 15.5 inches, so it's kind of not a traditional height fan coil, but not a low profile fan coil. It sits in between. And it has a lot of options. So it does come with a fresh air inlet, which is rear mounted in a mixing box. So that's really a big benefit for these DOAS systems we're talking about. It comes with 2-inch thick MERV 13 filters, and it comes in a number of sizes to offer and deliver, whatever the CFM is required for the zone. So we see a lot of this in lab and life science. We see a lot of this in office. We see this in some markets in high performance schools, and we see this predominantly in exterior zones that require higher loads. So pretty common product. Another one we have is the BCHD product. So this is a cool product. It's a newer one for us, and this is a direct drive blower coil. We have a 3-phase version of the motor coming soon. Currently, it's only single phase, up to 4,400 CFM. It will be up to 4 inches of pressure once we release that 3-phase motor. We're going to be the first manufacturer to market with a 3-phase ECM motor in this range of horsepowers, which is pretty exciting. And this one's pretty great. It's like an indoor air handler built for lab and life science type work. You know, solid metal liner options. Once again, fresh air inlets, in this case on the side downstream of the cooling coil, which maximizes the log mean temperature difference of that coil, essentially keeps the difference of air temperature and water temperature as large as possible, which is going to allow for more total capacity. Silencer options and factory mounted piping packages on this as well. Now, one of the key things with all of these products, and it's a key design choice that we've made, is to have 2-inch thick filters whenever possible, 4-inch thick filters in some cases as well. I see two trends in the HVAC industry that are trains that will not stop. We need better indoor air quality and we need more energy efficient systems. And those things are in opposition to one another. So that's going to be real fun and interesting for design engineers to come up with solutions. And that's true for product designers as well. And our version of that is thicker filters. Can anyone tell me why is a thicker filter better for indoor air quality and energy efficiency? Yeah, absolutely correct. So for everyone online, Ken, my favorite man in the audience today, because he's got answers for everything, said lower initial pressure drop for the same level of filtration, and that's absolutely correct. These filters are typically pleated, right? So HEPAs are pleated, MERV 13s are pleated, MERV 8s are pleated, and the thicker they get, the larger the effective surface area is, which actually means we're going to get lower pressure drop even though the filter is visibly larger. It looks like it should provide more, but it provides less. And we can see that on the curve here. You know, the same filter, I'm looking at the 1-inch, 2-inch, and 4-inch version of the same filter media type for a MERV 13 filter at 250 feet per minute of face velocity. We're looking at like 0.8 to 1.2 to 1.8. So significant differences in initial pressure drop, which is going to mean we can have more air changes, more air passing through a filter, better indoor air quality, and less energy cost. The other thing we do with all these products is we throw the biggest possible blower we can, because most blowers are happiest and healthiest running at about 1,000 RPM. So we can even see with our low profile fan coils, we get a big clamshell blower that has a tighter kind of profile. We flip it on its side and we situate it in the unit like that instead, which allows for much better fan operation as well. So quickly here, I want to talk sound considerations. And the big thing for sound considerations for any product that has a coil and a large return opening is there's going to be multiple sources of sound. They're going to drive acoustics, and they're going to be very close to a big hole in the casing of the unit. So if we see a coil, think of that coil as a hole for sound to travel through as well. So what we need is something to stop sound but allow for air to travel. And for us, that is a silencer, and in this case, an integral silencer. What we have up top is our version of this product versus a rough sketched out depiction of a competitor's product. The difference here is silencer position with respect to the coil. And if we actually have the silencer on the outside of the coil, it won't show up in the catalog, but it can lead to localized velocities that will cut the effective surface area of the coil and reduce capacity. So we tested it, our silencer, in both configurations, upstream and downstream of the coil, and we found that it could have up to an 8% difference in capacity. But because of the way these products are certified and cataloged, it won't show up on a catalog page. So we chose the version that is better for performance, more expensive for us to ship. We obviously still have to compete with market competition, so we trade off margin for capacity, but that's a worthwhile cost because we want to make sure our products actually work and do what they say they will. So this kind of goes more broadly to the discussion of close coupled silencers and quiet terminals and fan coils. So a show of hands or give a thumbs up in the chat for those of you online. Can I take a terminal off the shelf, smack a silencer on the end of it, and will it perform the exact same as an actual fully tested integrated assembly? So hand up if you think yes, they'll perform the exact same. Thumb up in the chat. Or hand up, I guess, now if you think no, they'll perform differently. Love to see all the hands up in the room. Yes, they are not equal. Appreciate it, everyone. So the rationale for this is test method. And when we look at ASTM E477, which is the silencer test method, the way we actually get a catalog insertion loss is we're going to have a known source of sound, which is going to be discharging both air and acoustics down an open piece of ductwork. And we're going to measure that sound power value in a reverberant room. We then replace a section of the duct with a silencer. We measure again, and the difference in measured sound is the insertion loss of the silencer. Does that make sense? So we start with the greater magnitude, measure the lesser magnitude, thanks to the silencer, characterize the changes of the silencer's performance. Now, critically, this test method also has 5 equivalent duct diameters of straight duct upstream and 10 equivalent duct diameters of straight duct downstream. Fortunately, good silencer manufacturers will have rules of thumb that will help adjust the criteria for bad inlet conditions. And usually you get effectively the same performance as long as you have 2 equivalent duct diameters of straight upstream rather than 5. Or you can use an elbow silencer, which helps to eliminate these concerns as well. Now, when we test as an assembly, we actually just put the whole assembly together and measure how much sound it generates. We don't worry about insertion loss. We're trying to make a quiet terminal, not a loud terminal with a silencer behind it. And there's a good example of this that we actually researched and studied. So the thought process here is we can take our terminal unit sound power value, we can subtract the silencer insertion loss, and we should be able to calculate out the performance that we're actually going to achieve. However, we tested this in the lab at a close coupled condition, 1 duct diameter, 2 duct diameter, 3 duct diameter, all the way to 5 duct diameters to quantify how much install condition actually influences the sound power value of the assembly. And the testing showed that a silencer can end up being a kazoo if you place it directly on the end of a terminal unit. The thought process is turbulent air and localized velocity hits the nosing of the silencer and it generates more sound than it dissipates. I've seen this on an actual project in New York. We were base of design on that project. A contractor pitched a standalone silencer and a terminal from another manufacturer. They put them directly on the units. The space was very loud. We showed up to the job site. There was a terminal and silencer graveyard in the parking lot. We ended up going in and making some recommendations to actually keep as much product as they could, as long as they could move it downstream. And then they replaced back to base of design for all of the products where that wasn't possible. So this is something that gets specified a lot in this market. This is something that the Buckley team is extremely capable and intelligent to assist with. The reality that taking a standalone silencer off the shelf and putting it on a noisy terminal might not perform as you expect. So that's why this market likes the STVQ. This is a very acoustically inclined market. We see more sound power values than we see NCs here, which is great. We see a lot of silencers or attenuators close coupled onto products, which is great. Now, I did note 2 equivalent duct diameters previously as a rule of thumb from noise control manufacturers. We can see that quantified here. We get equivalent performance, but it does take the full equivalent 5 duct diameters to get the exact performance we would expect. Any questions there? So this is how we actually do it. It's all construction based. We do lengthen the distance a little bit between the silencer baffles and the inlet. We play with that a little bit in our design. So we cut a little off the inlet. We move the nosing of the silencer a little deeper into the actual silencer casing. That helps with creating some normalized airflow velocity. More importantly, we optimize the silencer free area for every unit. So essentially we tune the silencer to the valve size. What I mean by that is a 4-inch single duct doesn't get a 4-inch free inlet, free area silencer. A 5 with a 5, a 6 with a 6. We tested the whole fleet. We did CFD analysis to play with it to try to create as little turbulence as possible to maximize insertion loss and minimize generated noise. And then we also have this tapered surface, which some silencer manufacturers can't even manufacture or provide. And this helps provide some static regain. So it's really what we would quantify at prices like a medium velocity silencer. When we look at this on fan powered units and fan coils, really the big thing we try to do is airflow match the geometry. So in this case, a double width, double inlet motor blower assembly is going to throw air down kind of like a water wheel It's very directional. And so if we match the baffles with that directionality, we'll get lower pressure drop and better performance. The size 50 FDC, which is one of our products, its airflow range actually goes up when you put a silencer on it because it's better than an open duct condition. We don't catalog it though because it would just confuse everybody. So we keep it the same, but it actually is a better condition than an open ductwork. Okay, my last piece, we're going to run through this quickly and then I'm going to throw it off to Chris, but I wanted to talk a little bit about hot water coils, especially considering low entering water temperatures. Who here works on designs, lays out hot water reheat coils? Okay, great. Who uses these equations on screen with a show of hands? Me too. They are great equations. They're great equations that sometimes when we also look at like AHRI certified performance from a manufacturer, they don't always line up and it leads to resubmittals. So who gets annoyed with resubmittals and redlining submittals from manufacturers and reps when they get performance back? Nobody likes it. And unfortunately, it's not Sean's fault or anyone from Buckley's fault, and it's not you as the engineer's fault. But I just want to talk about why it happens. And then I'm going to talk about a tool once Chris is finished that can help fix that problem. So I like to look at the actual calculation. And once again, this is kind of cookie cutter ASHRAE stuff, but it helps paint the picture. So what I'm looking at is a zone heating load of 9 MBH roughly. And if I'm assuming some temperatures like a 75-degree exhaust and a 90-degree supply air temperature, which is within a 15-degree delta T, which is going to mean essentially that I have a good ventilation effectiveness in design day heating conditions, I could be looking then at a supply air of 550 CFM to offset that load. 550 CFM of 90-degree air is going to keep my space comfortable on design day. I can then plug that into a coil capacity because I know I need to reheat my coil from 55 degrees up to 95 or up to 90 degrees in order to make this work. And that's 21 MBH that I'm going to need of coil capacity to achieve that load on design day. I can then take that output, 21 MBH, I know my leaving air temperature, I know my entering air temperature. I need to figure out my hydronic side as well. So I take 21 MBH. I know the supply and return water temperature I need for my condensing gas boiler. It's 140, 120. I plug that in there. I get my GPM. Bada boom, bada bing, a perfectly scheduled hot water coil. But I don't get this performance back from a manufacturer. Is anyone familiar with this kind of workflow? Has anyone seen this kind of thing before? So the reason why this happens is because there's actually a third equation, which is the coil capacity, which is dependent on the log mean temperature differential we have through the coil, a complicated equation that just tells us this is the average difference in temperature between my water side and my air side for the totality of the coil. Log mean temperature differential is also the reason and the rationale why we want counterflow heat exchangers, not parallel flow heat exchangers. I know that was a fluids lab that I did during my engineering degree. I'm sure somebody else in the room has had similar experience. And so what we have is the capacity is equal to the log mean temperature difference of the coil times two different coefficients. The first is the coil heat transfer coefficient. And this is based off of the material and the construction of the heat exchanger and the fluid velocity through the heat exchanger. So is it laminar or is it turbulent? We then also have the coil area, and this is an effective face area. So this isn't just the height and the width of the coil. This is how many fins per inch I have. This is the fin thickness I have. This is the tube spacing and the tube diameters. All of this comes out to an effective heat transfer area. So if I took a coil and I could make it any size with any material, I can make it always match the air side and the water side equation. And I actually did that. We can create custom coils at price. We can also purchase very custom coils from manufacturers. But what I wanted to compare was the engineering calcs, a 2-row standard coil and a 2-row high capacity coil. This is for a 10 and 12 fin per inch condition. That's what standard and high capacity means from price. I then wanted to look at a custom 2-row coil which means I can change my fin thickness, my fin spacing, my material type and composition. I'm also assuming that I can make the coil bigger or smaller. And what that's going to mean is I would need to have some duct transition to and from the coil, but it is possible. Can anyone tell me why don't we take the approach of custom coils? Cost. A standard to a high capacity coil from Price, just on the coil, so not on the total single duct or fan powered box, just on the coil itself is about a 30% increase in cost. Anyone want to guess what is the cost increase from a standard 2-row to a fully custom 2-row water coil? 50% more. Anyone else? It is higher than 50% more. I'll keep us going in the right direction. 4 times more? It's more than 4 times more. It's more than 5 times more as well. We're getting close. This is spec'd out from me, from our coil OEM, with no margin or markup from Price at all. This is just the cost of the coil as we receive it versus the cost of the coil for us to make one. So this would be us handing it along without even making any money off of it, and it's 11.25 times more. Partially, probably the reason for this is to really dial it in, and I wanted to get it as close as I could. And this was as close as I could. I needed copper fins, which I'm sure is a big reason for the cost there too. But when we look at custom coils, we're looking at swapping over a full kind of commodity style manufacturing facility to a job shop, and that is expensive. So that's why we see a trade-off where we're going to have higher GPMs and lower delta Ts, or lower GPMs and higher delta Ts. We're going to get close, but it's because we don't have full control over the way we make the coil.